Yang tanya, Hello. If you've joined the chat, then can you give me some confirmation that you're watching? There's only two people I see right now. There's just one other person. Yes. Oh. Okay, cool. So, Guacamole, are you the only one watching the session right now? Oh, there's four people. Okay, cool. There's at least somebody watching. So I'll get started in a few minutes. Maybe someone else will come. Seems less busy than the previous session. Okay, I'll start the session now. Uh, Whoever's watching, I think there's like three people. That's fine. I'll start the session, and if you have any questions, you can ping me in the math channel, and I'll respond while I'm doing the session. Okay, so the first topic is trigonometry, which we're going to cover right now. Is topic 3, which I was going to do on Tuesday, but I'm doing it right now. So whatever's in bold on this page here, that's what the HL content is. But some of the stuff is is for all people. So the first thing that I can get into is radian measure. So um, if I open up, it's basically, instead of using degrees, you'd use radians, and you have a circle, and as you go around, you'd call that 2 pi radians. We define this the circle in terms of 2 pi because the arc length of a circle with radius 1 would be 2 pi around, right? So if we were, say, if we had a circle and the radius was 1, and we wanted to find the circumference, it would be 2 pi r, which would just be 2 pi. And that's kind of how we do it around the circle. And then multiples and factors of 2 pi, when you divide them, they give you different sectors of the circle, and they give you different portions of the circle. Notice one important fact about the fact when we start defining it in terms of 2 pi r, we come up with a very useful formula for the arc length of a portion of sector of a circle. So what you would do is you would notice that the arc length of any circle, set of a circle, is the radius times the angle at which you're sweeping out. Now, the easiest way to check if this works is to check it with the whole circle, the circumference. So if you were sweeping out 2 pi radians, which is the entire circle, then multiplied by the radius, right, you would get 2 pi r, which is the circumference of a circle. So that works. And you can go in and check if this works correctly for other angles, just to convince yourself that this works. But this is super useful, and it gets stuff done faster in certain problems. And if you understand this, then that's good. And if you want to find a way to understand this, you should try and think about why the circumference of a circle really is 2 pi r. Think about how that connects to radians, and the fact that 2 pi radians times the radius would give you this formula. So yes, there's that. And then there's areas of sectors. So in the same way, you would when you're taking, you would make sure that you have the radius is pi r squared, but then you have to divide it by whatever multiple of the angle that you have. So if you had like pi, you'd have to divide that by 2, and so on. So that's pretty self-explanatory. You can try and mess around with it. I'm not going to give you a specific way to do it, but whatever feels intuitive during a test as to how you do it. And sometimes the best way to do that is to find out the area of the whole circle, then find some multiple and divide it and calculate the area of a sector. So yeah. Next is the definition of cosine, sine, and tan in terms of the unit circle. Now, I find the unit circle to be super helpful and super useful, and you should always use the unit circle because the unit circle it'll basically tell you it's something that you'll never have to memorize, and you'll only have to memorize it if you make it so that you're memorizing it. But if you understand what's happening behind it, it'll make all of your trigonometry work much easier. Like your entire life will just become easier. In fact, in a test, I don't memorize any exact trig values. I don't memorize any ratios or anything. For some reason, I always keep coming back to the unit circle, however much I have actually done the topic, and I find that that's very useful. So let's just look at what the unit circle really demonstrates. So there's a circle around here, and this one point which I've marked over here is on that circle. I'm not going to draw the circle because my circle drawing skills are really bad, and I don't think it would be very useful for you to see my really bad circle. But here, say this point is on that circle, and we had some angle theta, which is reaching out to that circle, which is like there. And basically what we know is we would use our trig ratio. So what we would know is that sine, and we would say that this is length 1. The hypotenuse is length 1. It's a unit circle, right? So it's a unit, and 1 is the most arbitrary unit right over here. And what we would say is that we would say sine of theta is equal to the opposite, this side, over the hypotenuse. So the opposite over the hypotenuse, which happens to be 1. And then what you would be able to figure out is that the opposite, this side over here, is actually equal to sine of theta. And so you could put that in over here, sine of theta. This length is sine of theta. And then you can see on this side over here, you can do the same thing with cosine of theta is equal to the adjacent over 1, which shows you the adjacent is equal to cosine of theta. And then you would know that this side is cosine theta. This leads to an important fact, which is that this coordinate actually has points x, y. So you would do cosine theta, sine theta. That's what this coordinate is on the unit circle. And basically almost what the entirety of the unit circle is doing is trying to find these coordinates. So you would know the values of cosine theta and the values of sine theta depending on how you're doing the coordinates and with the unit circle. There's different ways to think about how to calculate these things, but this is what the actual definition of sine theta and cosine theta is. It's the length of this side. And that's how we define sine theta as in terms of the unit circle. That's how we define cosine theta in terms of the unit circle. And then obviously we have tangent of theta. So what we would do is we would do opposite over adjacent. So we wanted to know what that is. And then that would be tangent of theta, which is also happens to be equal to sine theta over cosine theta. So if you see just from the unit circle, you have a series of facts that you're learning. And these are facts that if you completely understand the step between each one, why we're doing these things, it'll be really easy for you to rederive these in a test. So say you forget a certain property, and you'll be able to understand how this is working over here. So yeah, one sec. I think one more important thing that I have to mention related to this is that this is a very important triangle for the reason is that it leads to the development of almost all the trigonometric identities we know, specifically because it's a right triangle, this one. So on this point of the circle, we drop our perpendicular, so we have a right angle over here. And because it's a right angle, we can use the Pythagorean theorem, which is a squared plus b squared is equal to c squared, where a and b are the two sides and c is the hypotenuse. And we'd be able to derive that sine squared of theta plus cosine squared of theta is equal to 1. Once we know this fact, everything just sort of clicks into place. So you can divide these by different things. You can manipulate them in different ways, and eventually they'll actually give you a series of trigonometric identities. And I think for this is let me check. Let me just check that. Yeah, so I'll just get it. So this is HL material. So if you're an SL, you might not need to do this, but this is HL. Note that for SL, if you are going to be doing any calculus in university, so like courses related to like maybe physics or just any calculus, this might be useful. You might be learning this. The IB doesn't require you to, but maybe uni will, so this could be useful. So this is secant, cosecant, and cotangent. And we'll understand what those are right in a second. So those are just the reciprocals. So what you would do is that you would have 1 over sine theta, which happens to be equal to the hypotenuse over the adjacent, and that we call the cosecant of theta. And so the same way we have 1 over cosine theta is equal to the secant of theta. Now, the way that I remembered this, like I don't really think there's a way for you to memorize, like derive this like name on your own. It's kind of confusing which one is which. The way I remembered it is that I always associated sine theta with secant theta and cosine theta with cosecant because they started with a C and they started with an S. I just said that's not how it works. Like my way of memorizing was that this is unintuitive and doesn't work correctly. And that's how I always remembered. You're always going to have the opposite letter because these are stupid. I don't know. There's a reason why it's called cosecant and secant. But I don't think we should get into that over here. Just try and make sure you can remember these. Actually, it might be in the formula booklet. I'm not sure. I haven't really used it, but I just keep remembering this. And yeah. So when we use these, we can also derive more trigonometric identities over here. So what we also know is that if we divide everything through by cosine squared of theta, we would have cosine squared theta over cosine squared theta over cosine squared theta. Sine squared theta over cosine squared theta. Note that sine theta over cosine theta is tan theta, so this would be tangent squared theta plus 1 cosine squared theta over cosine theta is equal to secant squared theta. And now this is another identity that's super useful, which again, this is given to you in your formal booklet, but it's nice to know why this stuff is happening. Because sometimes they might give you problems related to this stuff, and they'll ask you certain questions that are specific to your understanding of this concept. It's better to also understand why these trigonometric identities exist. So so if you got the sets of reciprocal trig identities, and now calculating the exact values of different things. So the way that I usually calculate exact values, I never memorize them. I do know that there's these like special trig tables you have where like you put everything square root of 2 and you do some magic-y stuff. I never do that because I don't feel comfortable doing that. So let's just write this as 0, pi over 6. So there's a few different triangles I think I should just go over. So the first triangle is obviously the one with the angle over there. This is theta, is when theta is equal to pi over 4. So this is 45 degrees. So when theta is 45 degrees. So that means that if theta, this is 45 degrees pi over 4, this is and this angle, the 90-degree angle, is pi over 2. This must be theta as well. It's also pi over 4. And this is, if you note, this is an isosceles triangle. So this angle is equal to this angle. And if we were to say, and then how we would figure out the values of the sine of pi over 4, the cosine of pi over 4, tangent pi over 4, and so on, is by trying to figure out the properties of this special triangle over here, which is an isosceles triangle. So let's just set the hypotenuse equal to 1. And this side is x, and this side is x. What I would know is that x squared plus x, the square root of x squared plus x squared is equal to 1. So the square root of 2x squared is equal to 1. This is by the Pythagorean theorem. So square root of 2x squared is equal to 1. So 2x squared is equal to 1. And so then I would know that x squared is equal to a half. And then x is equal to 1 over square root of 2, but I can rewrite that as square root of 2 over 2. And if some of you guys were memorizing things, this is what you would have ended up with, the square root of 2 over 2. So x is equal to square root of 2 over 2, and this one is also equal to x square root of 2 over 2. Now, note the important fact that we learned earlier from our unit circle is that if you have any triangle with 1 and a right angle over here, this is sine theta, if this is theta, and this is cosine theta for this triangle right over here. And now that makes sense because now you know that the sine of pi over 4 is equal to this side over here, so which is sine theta. So that's equal to square root of 2 over 2. And then this side over here is equal to cosine of pi over 4, which is the square root of 2 over 2. If you want to think about the definitions in terms of what the ratios are, so then you would look at this is theta. I want sine, which is opposite, over hypotenuse. So square root of 2 over 2 over 1, which is square root of 2 over 2. If I want a cosine adjacent over hypotenuse, it would be that way. This is how I would know what the sine and the cosine of 45 are. I don't actually ever know. I don't actually ever memorize anything. It slows it down sometimes, but if you're able to do this efficiently, like eventually you practice enough with this method, this process will get embedded in your head. Obviously, we can also calculate the tangent and then the secant and everything. So tangent would just be sine over cosine. Since sine and cosine are the same, tangent of pi over 4 is just 1. And a faster way to know this is the tangent is opposite over adjacent, and the opposite and the adjacent are the same because it's an isosceles triangle. So this must be true, and it must be 1. So now that we have pi over 4 out of the way, we can look at the next one. So we have the pi over 6 and pi over 3 triangle. That is a triangle which is the 30, 60, 90 triangle. So let's just make this like that. So I'm gonna keep it in radians so we get used to the concept of doing it in radians. And that's pi over 3, pi over 6, and pi over 2 angle. The way that we would do this is you have to detect that it is half of an equilateral triangle. because if you know this is 60 degrees, this is 30 degrees, this is 90 degrees, and there's an equilateral triangle right over here, which has a pi over 3 over here, and since it's a reflection, this is also pi over 6, and this whole thing is pi over 3, so it's an equilateral triangle right over here. So that's key to figuring out how to solve this triangle. Now, what I usually like to do for this triangle is that instead of using a instead of using 1 as my hypotenuse, because this one it gets kind of confusing how the stuff works. So I don't like having it in 1 because then you'll end up with a whole bunch of fractions everywhere. I just try and figure out the ratio by putting a 2 over here instead. So let's think about how this will work as an equilateral triangle. So since there's a reflection on this side, and this is the side that's getting reflected, this should be half because it's a half of the actual triangle. So this should be a 1. And that's kind of why I keep it like this. Keep this 2, so this is a 1. I don't like having this 1 and this is a half because I just don't like fractions much. But that's whatever is up to you. So then again, we use the Pythagorean identity. So we would have so we have 4 is equal to 1. 4 is equal to 1 plus c squared. C squared is equal to 3. C is equal to square root of 3. And yep, that's it. That's your triangle right over there. And then you can derive all the properties. Once you figure out this is what the triangle looks like, you can derive every single property that you need to know. So you would know the sine of pi over 3. This is the pi over 3 angle. Look at the opposite. Square root of 3 hypotenuse. Square root of 3 over 2. Pi over 6. You look at the sine of pi over 6. You look at opposite over hypotenuse. Sine pi over 6, 1 over 2. And that's how you would figure that out. And this is super useful. So make sure you know this triangle. Oh my God, that was a horrible circle. Make sure you know this triangle. This is an important triangle. And it's good to know this. Don't sit and memorize exact values. Obviously, this is what's useful in paper 1 for you able to do this quickly and to be able to find your things first. You don't want to just know it wrong. It isn't good. So now let's look at some of the other ones, which is 0 and pi over 2, because we've done these 3 right over here. 0 pi over 2, 0 pi over 2. So let's look at so for 0, this is an interesting because we need to think about what's happening when we actually have a 0. So I'm just going to draw a small tiny triangle over here. And this has some x which is approaching 0. So this is becoming 0. So this is like tiny over here. And this is 1 obviously. And this is also 1 because if this is becoming 0, these two lines are just becoming the same line. And this is what theta is. So that's theta is equal to 0 as well. So when we would look at the sine of 0, we would know that because it's closing in, like it's becoming smaller over here and it's becoming tinier, we would know that this is 0, this is 1, this is 1. The sine of 0, opposite over hypotenuse. 0 over 1. Sine of 0 is 0. Cosine of 0 is equal to the adjacent over the hypotenuse. So that's 1 over 1. Cosine of 0 is 1. The tangent of 0 is equal to sine over cosine, which is, again, 0. And that's it. Note for HLs that the cotangent of 0 is undefined because the cotangent of 0 is 1 over 0 because it's the flip of tangent. So 1 over 0 is undefined, and we don't say it's infinity. And especially if people go into calculus option, you can't just say things are infinity. That doesn't work like that. You need to say it's undefined if you reach something that's reaching infinity. Then for the derivation of the last angle, which is check. I don't know how I forgot this. Yeah, pi over 2, which is 90 degrees. So 90 pi over 2. So the way we look at pi over 2 is that again we have a tiny triangle over here with like a right angle there, and it's getting smaller and smaller. This side is 1, this side is also 1 of the triangle, and this is becoming 0. So now you look at sine of pi over 2, which is equal to the opposite of hypotenuse, which is now is equal to 1. Cosine pi over 2 adjacent over hypotenuse is equal to 0. Same thing. We've got all the things related for this. Now, if you know how to do these things, this will become easy for you. You'll be able to think about any angle, any triangle. You'll be able to immediately find out what the exact value is. Now, one important note is that sometimes we don't exactly get the original triangle or the original angle. In which case, we need to start thinking about what the signs are. So, because sometimes we have angles that are much larger than the original triangle. We have obtuse angles. So the way we would think about those is let's give one example, which should be able enough to understand all of it. So we had pi over 3. So the normal pi over 3 would be right over there. We'd have a pi over 3 over here. That's a 60-degree portion right over there. And as such, that could be 2. This would be 1. This would be square root of 3. This is fine as a triangle, right? But say someone gave us not pi over 3, but they gave us 2 pi over 3, right? So now this is, if you notice, this is 120 degrees. So it's another pi over 3 in this direction, and it looks like this. So this is 2 pi over 3 right over here, 2 pi over 3, and this is just pi over 3. And we can make the exact same triangle here. So this is 2. The length of the hypotenuse is always positive. It's 2. This is square root of 3 because it's the same triangle reflected. Square root of 3, and the height over here is positive. But notice now this length over here is 1 because it's in the other direction. So this is a -1. So this triangle is in the -1 direction. Now, if you are able to notice that this is the case, that this is a -1, it's a negative integer in that direction, you will not have to remember what are the signs of each trigonometric function in each quadrant. You'll be able to know this is what the unit triangle, this is what the triangle gives you, and follow what the triangle says. So now notice that the cosine of pi over 3 was adjacent to hypotenuse of 1 over 2. But now the cosine of 2 pi over 3, which is all the way over here, is -1 over 2. And the same for the tangent, it changes sign as well. But the sign of pi over 3 does not change its value. So now you could also do the same thing if you go into here and we say this is pi over 3, right? And we had the triangle over here. You do the same thing, but now this is also negative. This would be a negative square root of 3, and this would be a -1. And if that makes sense, so yeah. Okay, I got people watching. So yeah, that's how you would think about their multiples. I like to think there's another way to actually like think about the values of like 0, pi over 2, pi, 3 pi over 2, and 2 pi, is to think about the graphs of these functions. So when I think about sine, I know the period of sine is 2 pi. So I know that if we drew a sine curve like that, that's a horrible sine curve. If we drew a sine curve like that, this would be at 2 pi. And then we know that because this is the same as this, it's like just flipped over, this is the halfway point, so this is pi. And then I would know that there's a peak over here at the halfway point as well, so that's pi over 2. There's a peak over here as well at the halfway point, that's 3 pi over 2. So now all of these I have graphed onto a curve. And then if I wanted to know any of the values of these, I know that sine is bounded by 1 and -1. So I'd be able to quickly figure out the value. So if I wanted to know pi, I'd know for the sine function, pi is indeed 0 because it passes through the x-axis at that point. For 2 pi, it's the same case, and then I would know for any n pi, it is equal to 0. The sine of any n pi is equal to 0. So for any value of pi, it would do the same thing because it would cycle back. And then for pi over 2, I know that is 1. And for every 2 pi, it'll also be 1. And for 3 pi over 2, it's -1, and every 2 pi, it'll be -1. If you just keep drawing the same period over and over again. Now, you can use the same logic, the exact same logic for cosine. So you could draw. Try to utilize a new eraser feature that I have. That works pretty well. To be fair, yeah. So the cosine starts at 1, and then the cycle goes like that, and it ends over there. And that point over here is 2 pi at a peak again. So for the cosine function at 0 it is 1, and then at 2 pi it's a 1 again. But then at the center point over here, the negative 1 reaches at pi, and then between 0 and pi, the pi over 2 gives the 0, and the 3 pi over 2 gives the 0. So having the comfortable nature of these, being comfortable with these functions is very helpful. Because if you know how to graph these correctly, you can also gain a lot of information about the points, about like of their intersection points and things, and you'll be able to understand better the values of these points. And I can't stress how important it is that you understand how trigonometric functions are bounded between different values and what their properties are, especially when you get into the calculus option, if you're in HL. And then we have the double angle identities and the compound angle identities. So I don't really feel like there's much need in even explaining how these work. They're in the formula booklet, and they're right here in the formula booklet. I don't know if they're in SL. I'll have a check. Okay, they don't have. Yeah, you have some of them. There's some ways to use them that I'll explain. So, yeah, so this stuff is all in your booklet, and you have the compound angle stuff. It's all in your booklet. I think compound angle, yeah, that's compound angle is HL. But so some interesting things you can do with the double angle identity that also become more important when you're going into calculus. So if you have anything that has a if you have anything that has a if you have anything that has a cosine 2 theta, and you can always convert it to a 2 cosine squared theta minus 1 in calculus, which is easier to integrate. I think. 1 second. No, it's not easier to integrate. If you have a cosine squared theta, it's hard to integrate, and you want to move it to make it a cosine theta. So this leads to an important little discovery over here. So this one's pretty important. So if cosine 2 theta is equal to 2 cosine, IB expects you to know how to do this. A lot of questions will use this. So cosine 2 theta is a 2 cosine squared theta. Rearrange for the cosine theta. So what I would do is I would make it 2 cosine squared theta is equal to cosine 2 theta plus 1. And then I would divide everything by 2, get rid of the 2 there. And then I would end up with cosine theta is equal to square root of cosine 2 theta plus 1 over 2. This is super useful, especially because you've converted the double angle identity into the half angle identity. So we would think about it as the half angle identity is that if you wanted to know cosine theta over 2, you would evaluate the square root of cosine theta plus 1 over 2. And this is important. This is super important. What the whole thing I was talking about calculus earlier is related to this little function here. This is for HL. When you have cosine squared theta, it's not always easy to calculate what the integral is, but it's easy to calculate the integral of cosine 2 theta plus 1 over 2. This is not hard to integrate because it's just two. You can separate into two values, and it's just a cosine and plus a half. So this is useful for calculus later on, which I'll explain in a later session, I hope. So know how to manipulate these. Sometimes it won't be exactly obvious what the manipulations are that you need to do, but feel free to play around with these. So this is why it's important to get some practice with trigonometry problems. You get in there and you just think about what it is that, like, if you see a problem, don't check the answer. If you don't know what it is, then just try playing around with what's given to you, and that will be helpful. So you'll get a better understanding if you play around with what's available, and it might take you some time, but you'll develop your own solutions to these problems. Okay, so okay, so I think now, okay, so I'll show you, so I hope that everyone knows what the graph is, but I'll just show you how we manipulate the trig functions. Actually, I think it might actually be more useful for me to show this to you on Desmos rather than for me to draw it because my drawing skills are less than amazing. It's very bad. So if I were to, this is something. Now note that this is something that you can do, because Desmos is open source. It's free to use, and you can play around, create something like this, and you'll be able to understand things really well, really quickly. So I'm just going to set this to 0 for now. And this is zero. So this is a regular old sine function, and basically what I've done is I've added. I'm just going to change settings to. Yeah, so I just changed the pi over 2 so I can see the periods correctly. The way that we manipulate sine functions is almost similar to the way, it's actually exactly the same as how we manipulate it for a function. Because if you noticed earlier, we developed a few different rules for how to alter functions, and all of those rules apply directly to trigonometric functions as well. So we have the first one, which is just stretching into the y-axis. That's a very, very simple one, which is it changes the amplitude of the sine curve. If anyone has any trouble listening to the audio, just tell me, because my finger might like rub over my laptop's microphone. So just let me know. So here's what the curve looks like. The A controls the amplitude. So whatever the value of A is, that's what the amplitude is. If it's 0, everything's going to be 0, and that's it. But you can have a wide range of amplitudes. So that's one thing. And sometimes in questions, so you'll have to measure the amplitude, what you would do is you look at the highest point, you look at the lowest point, you divide that by 2 to know what the amplitude is for this part of the thing as well. So you would do, so here you would do 1. So sometimes, because that's important. Because sometimes you'll have like really weird positioning, and it might not be clear what the actual function is, but then you just need to check what the difference is. So if I had like 2.7, this difference from here to here is 5.4, and then that would basically do it. Let's just keep this for 1 for now. And now let's look at B. So what the B does is that it stretches it, but in a different way. So what we're going to be doing, so we're going to stretch it in such a way that's like that's in correspondence to the x direction. So this direction. And if you remember about functions, whatever you do on the inside of the function, which is like to the x inside the function, is going to change in the inverse way. So if I would make b equal to 2, it didn't stretch it out like the a would have done if I made it 2. Instead, it squished it down. And this should make sense because you're just squashing all those y values closer together because you're asking the function to give you a higher value at a smaller point at f(x) that you give it. So this is what so you would look at, so for the inside the b of the sine, you're looking at a squashing of the thing. So if you doubled it, you would have squashed it. Now notice that you can also gain facts about the period. So if I change 2 to 2, you know now the period is pi. So depending on, so you can even figure out what the stretching or squishing is of a sine function, depending on stretching and switching of any function, depending on the period. So you could check if I were to give you like a random one like 5. You can check the period. So I'll look through here, look at the period, 2 pi over 5. So I know that the 2 pi was the original one, and you divided it by 5. So you must multiply the inside by 5, and that's what the period is. Sometimes they can change the period with some some whole number. So it'll be like 5 over pi. Then the period will be like no, it could be like pi. B could be pi. Multiply by pi, and then the period is like, if you notice here, period is 2. Then again, so you have to think through 2 pi, to get to 2, what you do, divide by pi. Let's keep this back to 1. Let's start with the function of the way, which is the c. So this is a translation. Again, if you notice, we're going to make that a minus c just there. Because that's usually how translations inside work. It will be an inverse of what. So if I took away c, it moves to the right. So if you notice, it's moving with the slider back and forth, and that's basically it. And notice one important fact is that the sine function is a 0, right? That's at 0. But if we were to move it across by pi over 2, you just got negative cosine. If you were to move it across the other direction, so that's negative pi over 2, this is the cosine function. So if you were to alter a function of a sine, and you were to add pi over 2, so that's a x minus pi over 2, so that's an x plus pi over 2, you would actually get the cosine function. And I think that's really cool. And that's a good like thinking of how it's happening, because you're like translating the function from here to there, by just moving it by that factor. Notice another important thing is that when you're applying these functions to it, you have to keep the x nested within the b. So notice that if say we had some scaling factor for b which was 2, and we also wanted to move it across by so we moved across by pi over 2. So we would actually have to say sine of 2 and x minus pi over 2. So you need to make sure you put it in brackets like that. The 2 covers the entirety of the function. This is not the same as sine 2x minus pi over 2. This is wrong, and it will give you the wrong function. It won't give it out. It won't do it the same way. You need to make sure that the scaling, the stretching or squishing factor is around the entire translation factor of the sine. So yeah, move it back to zero. This one, I guess the easier one is moving up and down. Just moving it up and down. That's super simple. So if you fully understand these concepts, apply them to problems, these will give you some weird looking sine graph, which you need to try and figure out what the actual sine function looks like, or even the cosine function, because they're actually equivalent. But usually the question will ask you. Yeah. Okay, is it better now? Guacamole? Is it better? Just tell me to put a note if it's slightly better. Because I think it's because my hand is hovering over my mic. Yeah, okay, so that's better. So usually questions will give you a weird sine curve. So the best way to find, now this relates back to when we were trying to find amplitude. So if I was moving this up like this, and I made the amplitude something weird, now you have no idea where the function started, where it ended, what it was shifted by, or anything. So you need to look at one of the points. You look at, oh, okay, that's a height of 6.5, and this is at negative 1.9. So what I would do is I would say 6.5 plus 1.9. That's an 8.4 difference from here to here. And then if I divide that by 2, I get 4.2, which is my amplitude. So I know the amplitude is 4.2, which means at some point from down this line, there's a 4.2. So if I would just draw that. At some point over here, this is a 4.2. And I know that I need to find out what this is. So if I found that the height over here was what was the height again? I completely forgot. 2.3. Yes, yeah, I would know this is 2.3 because this is 4.6. It was 6.5, right? It was 6.5. It was 6.5 up here. So I would know the difference is 4.2 from the center. So I know this is 2.3. The center of the sine curve with the line which is passing through is 2.3. So I know that D is 2.3. It's been pushed up by 2.3. And that's how we'd calculate for this sine curve. Then you could do the same thing for the squishing and the stretching. So you just think about what's actually happening to the function. You'll be able to understand this pretty well. Okay. Inverse trig functions. Okay, so this is strictly HL, and the inverse trig functions are they're a series of functions that I think I'm just going to show them on Desmos again, the graphs, because I don't think I'm really worth much in terms of drawing capabilities. So I'm just going to keep it like that. And the inverse functions basically say, so if we had like sine x So we had sine x, right? And say we knew the ratio. So what happens when you put into sine x as an angle? When you put in the angle, then it gives you a ratio that you want from that angle. But now, say you have the other way around. You know what the ratio is, but you want to find out what the angle is that ratio is going to give you. So you would think about. So you would have to find some way to take the inverse of this. If you remember how to take an inverse of a function, what you have to do is that you need to set, so we have y equals to sine x, we would need to set that as x is equal to sine y, which, which is usually fine, except that x equals sine y isn't a function. Because if you notice right over here, there's it doesn't pass the vertical line test. So it's not a function because for one value of x, there's several values of y. Actually, infinitely many values of y, which you do not want. You want to have an actual function that can take in a ratio and give you the angle. So basically, what they came up with is this little thing called the arc sine of x. And notice that it's only defined from here to here. So if we just remove these two previous functions, notice it's only defined from here to here. It only reflects the points on the axis from here to here, and then flips them around right over here, and then you get this function right over here. And this is what the arc sine is. And now if you thought about the sine x function, you looked at these 2 points, you flipped it over. Now you know that now you have here's a piece of information about this arc sine function and what it can do. So the arc sine is obviously in your calculator, so it's already telling you. Well, you can evaluate this almost directly. But now the important thing is the domain. So what is how much it can range from? So notice the domain is from here to here, and it can exist at those points. So this is going to be from 1 to 1. That's what the domain is of the arc sine function. I mean, -1 to 1. And then in terms of height, you would be looking at from negative pi over 2 to pi over 2. So that's what your height is for the arc sine function. From pi over 2, negative pi over 2, -1, 1. Now, the way you would remember that this is exactly how it is that you would either one, you can graph it during a test if you really feel like it. Otherwise, you could notice that the original sine function has a point which is like that through the origin, and there's a peak over here, which is at pi over 2. Another negative peak over here, negative pi over 2, and then you know that this is being inverted across the xy line because it's an inverse. And then you would know that the domain is going to be the exact opposite of whatever this restriction is on the arc sine. And then obviously you have a varying different things. We have the arc cotangent. Let's actually look at the arc cosine. The arc cosine is slightly different. It's up here. It's centered around this point right over here. And it makes sense that it's centered around there because the original thing was like this. We need to pick a little region for it to be flipped across. And the region that they picked over here is the region from here. I think it's down to here. So from here, they flip it across this xy line over here. You see that 0.739, 0.739. That's the xy line, and they flipped it across and put it point over there. And the domain for this one is from -1 to 1. It's almost from cosine and sine, both the -1 to 1. For the cosine, it's from 0 all the way up to pi. You could possibly have something that's from negative pi over 2 to pi over 2. You would always find a way to try and get it into this domain because it would look really weird if it was like that. And there's like a piece of the function sticking out over here. It would be weird. So that's what the arc cosine would look like. And then we have the arc tangent, which makes sense because this is what the original looks like. So just make another line that goes like that. And the points at which it could, there's asymptotes for this, which is pi and 0. So it'll be bounded by 0 and pi. And then it has a little intersection point at pi over 2. Yeah, that's basically it. It can take in every value inside this range. There's no bound on the domain. However, when x approaches infinity, it'll be 0. When x approaches negative infinity, it'll be pi. And that's basically all that's need to know about the inverse functions. That most of the time you should try and draw on your own and try to figure those out instead of like memorizing. I have a real aversion to memorizing, but maybe for this you should try memorizing some of the domain restrictions. It can get confusing if you're trying to do it in your head, or you're trying to like draw a graph and then literally try and reflect it. It's difficult. So yeah, solving trig equations in a finite interval. So this one is it's quite what they usually give you is like they'll give you. So let me think about this. I'm gonna come up with a question on my on the spot. So don't yell at me if it's wrong or anything. They'll say there's some function between pi over 2 and 3 pi over 2. So the notation they would use is they use varying notations. They might say like pi over 2 to 3 pi over 2 like that, like interval notation, or they might even say like that theta is bounded by these two, right? So these are the kind of tables they'll give you. They say theta is bounded in this thing, and say that these guys know that the sine of theta is equal to 2/3. Find cosine of theta. So the way that you would do this is that you would think about so this pi over 2 this is pi over 2 here. This is 3 pi over 2. So you know whatever the angle is going to be somewhere here. That's 2/3. So either it's going to be here, it's going to be here. So let's just think about where we're going to put it. So we're going to make a little triangle here. We're going to make another little triangle here. So what we do is we think of the sine theta, 2/3. Sine of theta, we know that's actually equal to the opposite over the hypotenuse, right? And this is pretty. Okay, 1 second. Yeah. Okay. Cool. So you do the opposite over the hypotenuse, and that means that the opposite is 2 and the hypotenuse is 3. You can just equate those things. So you know the hypotenuse is 3. Hypotenuse is always positive, so that's 3. That's 3. You can't argue with that. And now you think the opposite is 2. So the opposite is a plus 2. It's a positive 2. So that automatically it can't be this one right over here, because that's a negative 2. So it can't be this triangle over here. And so it's this triangle over here. It's this. This is what your theta is. So your theta is sweeping out from here to here. It's between pi over 2 and 3 pi over 2. Has the opposite of 2 and a hypotenuse of 3. So you draw that triangle, and you would figure out what it is. And then if you wanted to find cosine, you need to find the adjacent. So if this is your theta you're working with, you need to find the adjacent, which is this unknown side over here. We can solve for that using the Pythagorean theorem. So we know that that is 3 squared minus 2 squared, which is equal to 9 minus 4, which is square root of 5. So that is the square root of 5. So the cosine of theta is equal to the adjacent over hypotenuse, which is, that's equal to the square root of 5 over 3. And that's how you do it. So you never actually have to use the arcsine function. Notice you don't have to go scramble for your calculator, like arcsine of 2/3. You're going to get some weird number. And especially if you're in a paper 1, then you can't do that at all. Because there's no way for you to possibly know the arcsine value for 2/3 without a calculator. Unless you're a genius, but you'd just be stupid for even trying that. But you should figure out how to use triangles to solve these questions. This is very common. There's always a question something like that looks almost identical to this. Like, I'm pretty sure this is the location I came up with. I've basically seen it before. That's why I came up with it so quickly. But yeah, so this is common. Get used to drawing triangles and figuring out where triangles are located. Yeah, so this domain restriction business was actually important because there's another triangle that also satisfies all of these properties, which is this triangle here. It has a 2 and a 3, and this would have been a positive sine theta as well. That's why it restricted you to pi over 2 to 3 pi. They wanted you to find this triangle instead of this one over here. They didn't want you to find this one. They wanted you to find this one. That's why they gave you the restriction, and they gave you the correct signs for the opposite and the hypotenuse. Yeah. So let's keep going. The sine rule. Cosine rule layer triangle application. Okay, yeah. Um, there's a little note from Andrew over here about GCSE topic. I'm not sure what he means by that. I've not done the GCSE, but I can explain the other rules. Let me check if there's anything here. Okay, cool. That's cool. Let me check the stream. Okay, cool. So sine rule. Okay, so the sine rule states that for any triangle, we have A, B, C, and the opposite side, which is A, B, C. The basically states this. It states actually this is also I'm just gonna check it's in your formal booklet. I'd rather write it exactly how it is in the formal booklet. Sine rule. There. I'm gonna write it like the formal booklet does, rather than my way. So, oh, that was not what I intended to do. Back. So A over sine of A is equal to B over sine of B equal to C over sine of C. So this is useful for a multitude of reasons. So if you know an angle, if you know like two angles and you know one side, then you can find the other side. Then once you know that side, you can sort of figure out the next side with some other information as well. So that's that. This is how you would use. So if you had like they gave you this angle, and they gave you this angle, and they gave you, and they say they gave you A, they gave you A, and they gave you B, and they say they gave you B. Now you can find what A is. Now that you know what A and B is, you know what C is, and then once you know what C is, you can also calculate what this one is using the final part of the formula and equating it to the previous ones. So this is a multifaceted rule. So you can use it like almost everywhere. So always you have a triangle problem, like some kind of problem. Just immediately think of, does sine rule do this? Can it give me some information about how to solve this problem? Yeah. And then the other one is the cosine rule. So this one is an extension of the actual. It's actually an extension of the Pythagorean theorem. So it's like a generalization of it. So this is your angle, your hypotenuse angle. So kind of, it's like your hypotenuse. So if you know C and you know A and B, so this time you don't have to have a right triangle, but this is sort of what the sort of hypotenuse is. Because if you notice, so this is A squared, this is B squared, it's 2. If you know these two, and you know an angle here, right? If you know an angle there, and you know these two, you can use this formula right over here. If you notice that if that angle, which we call C over here, if that angle is 90 degrees, so pi over 2, so using radian measure, cosine of pi over 2 is just equal to 0. So this entire term just cancels out. That's how we know the Pythagorean theorem actually works, because if you prove this, you prove the Pythagorean theorem as well. So that's a 90 degree, that's an A, and that's a B, that's C, and then you get C squared is equal to A squared plus B squared if cosine of C is equal to 0. So yeah, that's one little interesting thing about this. You should be able to learn how to solve problems with this one as well. And then we have this little final property over here, which you'll understand more why this actually occurs and why this even exists in when we think about vectors. And this is coming. So I think they have the exact same formula like right below. I'm sure they do. This is just if you have a triangle, side A and B. This is C. Right over there, you'll be able to calculate the entire area of the triangle using this formula for this thing over here. I think there's a small little understanding of why this occurs down in the vectors topic, which I think that covers the end of the trigonometry and circular functions topic. So, if anyone was watching, I think there was two other people watching. Is there anyone here? Do you guys have any questions or anything to think about? Just let me know if everything's fine. You understood everything in the Discord or on the live chat, like whichever one. I'll just wait like a second. Okay, that's fine then. Okay. Um, I'm gonna just take like a 5 minute break. Um, and go have some like water, and then I'll come back and finish off topic 4 right over here, which is vectors. It's gets complicated. Um, so yeah, I'll come back and talk about topic 4. Give me like 5 minutes. I think I'll be back at like 11 o'clock. Um, yeah. So I mean, in 5 minutes, which is depends on what your time zone is. Yeah. Okay. I'll be back. Hello, I am back. Yeah, everything is going fine. I am back. The static is the air conditioning is like ridiculously loud in my room. So when I went on a break, I just put it on like ridiculously high speed so that it could cool down the room, and then I turn it off while I'm doing the session. Otherwise, you'll just hear static like all the time. Um, but I need to cool my room, otherwise it just gets too hot. Yeah. So I'll just continue with topic 4 now. I have a feeling I'll use GeoGebra a bit. So yeah, is there anything important coming through the type? Okay, cool. So I'll start the session. So the first definition of given vectors, I'm gonna make sure I'm just gonna do them in like in 2 dimensions. So I'll give the explanations of what all these things are in 2 dimensions, and then later on I think I'll extend them to 3 dimensions. But notice everything I'm saying here also applies to 2 dimensions. So if you had a 2-dimensional plane, so that's y, that's plus y, and that's x. A vector is basically a point on this plane that you reach that point, and it's like it's a point of the plane which has a direction and a magnitude. So the magnitude is how far away it is from the origin, and the direction is what direction it is, obviously. So normally, what we would do is you could dictate. There's 2 different ways you could dictate a vector, which is the first one. The first one is obviously you can just use it in terms of Cartesian coordinates. So you would do a, b. So if it was like actually x, y. So x, y coordinate. The way we would denote this in a vector notation is you would use x, y, like that. That's how you do it in vectors. But yeah, and there's that. So the other way you would do it is like you can have like a modulus argument form. So it's like r theta. So if you were watching the complex number lectures, you can also just denote this in terms of the radius of this and then the angle at which it's put out. But generally, we don't use this notation for vectors in IB. So we're looking especially at this form. So this is the important form that we're using. And note that this doesn't only have to have 2 elements. It also has 3 elements when you have a 3-dimensional vector x, y, z. And that's important. There's 2 different kinds of vectors that you can have. So you can have a position vector, so that's a point in a plane, or you can have a direction vector. That's specifically looking at like a direction. Like you can't exactly differentiate them just from looking at them. It's all about context and when they're used, and how what they mean. This becomes more useful when we're trying to describe vector lines. So how lines would work in vector notation, and that's why it's important to make this little distinction here about position vectors, direction vectors. So right now, what I've drawn over there is what I had drawn over there before I deleted it. Yeah, I took it back. Was a direction vector right over here. So yeah, so that's not so that the first thing is obviously the magnitude of the vector is this little length of the vector over here. And if you have some vector x, y, the length of that vector is x squared plus y squared, square root of x squared plus y squared. That's the Pythagorean theorem. And if you extend that to a 3-dimensional vector x, y, z, the same formula holds. So you would use square root of x squared plus y squared plus z squared, which I think is really cool that you just add a z squared term in there and you can like figure out the next one. So that's the third 3-dimensional length of any vector x, y, z. I think this is also in your formula booklet, so you shouldn't have much of a concern with that. The next thing that we know is addition, subtraction, and then the different forms of multiplication. So just delete that. It's for addition. So the way we add vectors, we have to add them tip to tail. So if you had 2 vectors, you would go from here to here, and then if you had a vector there, then you have another vector from here to here. Normally in like physics or in some other topic, you would have like these angles, and then you would have like a radius, and you'd have this other angle at this bearing, or like if it's the radius, and you gotta have to like calculate the x and y components, and then you gotta like figure out all those things. It gets very complicated to add vectors. Thankfully, it doesn't work like that in the IB because we use a completely different notation. This is the math notation, like a nicer one. We use this notation, xy. And it's super easy to add these because if we wanted to add some vector xy to some vector zw, like that, because they're already split up into their x and y complements, it's super easy to add them. You just literally add them, and you get x plus z, x plus z over y plus w. This is y plus w. And that's what the vector looks like, and it's super easy, super simple. And now now we're clear with this. So the same thing extends to any n-dimensional vector. So even now a 3-dimensional one with x, y, z, and z. What am I doing? A, B, C, or something like that. And you add them up, you'd end up with the same thing as right above over here. So then we can. That's addition. Same thing applies to subtraction, obviously. So you would just have it as a you could just put it as a negative. So yeah, and then you can also multiply vectors by scalars. So if I had like some vector xy and I wanted to stretch it by a scalar vector a, so if I want to stretch the vector by a, then I can just make that ax ay. That is perfectly valid. Depending, you can swap back and forth between these. There's not actually any like you need to put it in this form or this form. It's depending on your context again, which one you're going to be using. Now, the most important one, actually completely fair. I feel like I can't explain this anywhere near as good as what probably 3 blue and brown could do. So I don't think it's. I think I'm gonna explain it obviously in this revision session, but it would also be very helpful if you watch the 3 blue and brown series on linear algebra, essays of linear algebra. You watch everything, you should get a much better understanding of what the cross product is and what the dot product is and what they actually mean in a context, in context to matrices, which it really does help for SL and HL. Like it's very helpful. Okay, I'm trying to check a ping I have. It might be a ping that's useful or not. Oh, it's not a useful ping. Some random person. So yeah, I'm gonna try and explain first I'm gonna explain the dot product, and then also like what exactly the dot product might mean. So the dot product works is I'm gonna start big stuff in. So the dot product I think I can explain in 2 dimensions, but the cross product only really has a definition in 3 dimensions. So we start off because if we have dot product is basically dot then w, and this gives you xz yw. Neat, right? This is neat. You just literally multiply the elements across. This is what the regular so one second, actually wait. One second. So dot product so you multiply these elements, then you add them to these elements. So xz plus yw and so on. You can do the same thing with 3 dimensions, 4 dimensions, 5 dimensions, so on. Whatever you want. And that's the dot product over there. Now this formula, this actually gives yield to another interesting property, which is discussed and which is put into the formula booklet right over here, if I'm correct. Here. This one is super important as well. This happens to be equal to this as well. So if this is this is v, and this is u, right? And this is v. Then this is also equal to the magnitude of v times the magnitude of u cosine theta, which is the difference between cosine. Let me just check I got that right, because sometimes I don't always write what is needed. The angle between, look at the angle between v and u, you get cosine, you get theta. You multiply by the magnitudes of both of these and get cosine theta, and this is the formula for figuring out the dot product as well. This is also a dot product formula. The derivation for this, I'll try and give a small sneak peek to why this works later on, but first I'll just explain to you why this is important in IB vectors. So this is important because sometimes you know how to do this between 2 vectors. It's super easy. You just literally multiply and add. simple multiplication, simple addition. You also know how to do these two because it's just magnitude. You do it's a numerical sum, a numerical product, a numerical answer, which you can plug into here and you can plug into here for the magnitudes of each of these. Remember, yeah, so you have the magnitudes of each of these, and then you multiply them by cosine theta, which is the angle. Now the theta is the one that's hard because you can't calculate that very easily, so you can actually come up with like a little like an adjustment to this. So you would do cosine theta is equal to xz plus yw over the magnitude of v, the magnitude of u. This is what is really important to vectors. So you know how to do this stuff. You know how to do this stuff. Once you find this, plug in the put arc cosine of this, you'll get your theta. And that's why this stuff is so important over here, because you can find the angle between two vectors really quickly using this method. One note that I like to make, which I forgot to make right at the start of this little session over here, is the meaning of this little sign here, the absolute value or the magnitude or whatever you like to call it. In reality, all of our scalars, all of our the numbers that we have in our number system are also vectors. So if we on a one-dimensional line, so if we had this as 0 and 1, 2, and then -1, -2, if we had some number -2 and we plugged it into this formula, which is -2, this is a vector like that. What this means is the magnitude of this vector -2. So the magnitude is 2. The length of this vector reaching to -2 is 2, and that's why this is 2. And then the same. So basically, what this means is what is the distance to away from the origin. And then if we were to like have some other vector v in 2 dimensions, it's how far away from the origin is it, which is the length of that vector. That's just a small thing I like to say about dot product. Now, if you were to go and watch the linear algebra series on the dot product, what you would notice is that he discusses why this is true. He specifically discusses why this occurs, which happens to be a result of a certain mapping. So if I had some vector v and some vector w, what the dot product of these two vectors is the mapping of this vector to this vector and the magnitude of that. It's a weird little thing happening here, which he explains really well in his video, which you should definitely watch. If you find any of this stuff slightly confusing or why stuff like this is happening, that's very helpful to figure it out. So now I'd like to move on to the next little topic. So notice that everything over here I put over here is extended to 3 dimensions as well. So if you were to have a XYZ and a ABC getting dotted together, there would be XA plus YB plus ZC. So it all extends. So now the next topic that I'd like to look at is a cross product. So you look at those 2 vectors. Now the thing about a cross product is that it's actually more relevant what the cross product actually means in 3D space. And I think the actual explanation of what's actually happening isn't that bad. So if you had something like V and W, the cross product of that vector is the perpendicular from that line to out of the plane. So if we had like so what the cross product does is this. So it's a little formula for it. So V1, V2, V3. Yes, I'm going to denote the elements in here, and we will cross it with W1, W2, W3. The cross product is going to be, there's some combination of these. I'm not going to be bothered writing them all down. It's in the formula booklet how you cross product them. Whatever this vector is, it's like if we were to start at a point over here and then come out of the plane from here. So like towards, like out of the screen in towards you. Whatever that vector is, right? It's describing that vector. And the important fact about that vector is not just it's giving that perpendicular vector basically. It's giving the vector that's perpendicular to both of these lines. So that would be the 3D vector coming out of it. So the 3D vector coming out of the screen is perpendicular to both these vectors. That's what this cross product is giving you. And what's more important about it is that that cross product isn't just of any length. Okay, that vector, the coming out of the screen at the perpendicular to both of these, is not just any old length. It is the magnitude of that is the area of the parallelogram that these create. So if I had another vector, if I had the vector v written here, vector w written here, like you just took w, put it over there, took v, put it over there, the area of this right over here is the same as the magnitude of v cross w. That is the case. And that really, it should be like super cool. Like, how does that happen? So this parallelogram over here is the magnitude of the cross product vector in 3 dimensions. This also gives way to our little formula, which is if the area is the magnitude of v cross w, then the area of this little triangle here is half the magnitude of v cross w. So that's one way to find a triangle, the area of a triangle between two vectors in 3 dimensions. So yeah, that's super useful, and that's what the cross product is. The cross product is in your formula booklet, and that, so basically what the cross product is giving you is the perpendicular vector to both vectors in a plane. So I'm gonna try actually and like explain this in a GeoGebra way. So I'm gonna in GeoGebra. I'm gonna just come up with random vectors. So if I have 1, 1, I'm not sure how vector notation works in GeoGebra. Do they do it like this? Is that it? Nope, they don't do it like this. 1, 2. Is that it? But how do I make it a vector? Settings, projection, shapes. More. Oh, there we go. I think this is going to be a vector somewhere here. Yes, vector. Starting point 0. Okay, I don't know how this is working. I don't know how to use this. Let me see if I can just find a Google image that shows it. Yeah, this one I'm going to show you slightly, sort of. That's the vector here. That's some vector there. Look at the right angle, suppose the perpendicular shoots out that direction. We're going to look at this one. Basically, it creates a plane that contains A and B both, and then it gives you the perpendicular to that plane. Now, this plane idea it'll come into use a little later as to why exactly this happens, why exactly how we can utilize this to our benefit, especially for HL. I mean, only for HL. I don't even think I don't think that SL does this. Yeah. So we discussed scalar product. We've discussed the angle between vectors, how to calculate that using the dot product and what's in the formula booklet. I've discussed perpendicular vectors. There's one thing that I did not mention, that is if you have two vectors. Second. Okay, yeah, so if you have two vectors that are perpendicular to each other, the one that we can use is the scalar product right over here. You should notice that if the dot product, the scalar product of two vectors is 0, then theta must be 90 degrees, because cosine of 90 degrees, cosine of pi over 2 is 0. So this whole thing over here will just become 0. So the scalar product, if the scalar product is 0, the vectors are perpendicular to each other. And then, so that's you don't necessarily have to use this one. You can use this one right over here. So if you calculate this and calculate that this is all averages out to 0, then you know that theta must also be 90 degrees, which means they're perpendicular to each other. Okay, so the next little thing here is it's in the parallel vectors. So similar thing, actually, you can now then in the same case, if you have a have the cross product, which is over here, if the cross product is equal to 0, right? The cross product is going to give you. It means that they're parallel to each other. The two vectors that you have. So this makes sense because if you look right over here, this is another definition of the cross product, which is it's in the formula book. So you have to be able to know this is the magnitude of the cross product is also equal to the magnitude of v to the magnitude of w sine theta. Actually, I'm gonna just discuss why this is true. I think I already have it open. So this little thing is the area of the triangle V and W, right? Notice that earlier I said this is also the area of the triangle with V and W. So if we were to look at this, it would be the area is also equal to half V W sine theta. That's also true. The halves cancel out. The cross product is equal to V, the magnitude of V, the magnitude of W times sine theta. That's why it becomes useful back again in vectors. So that's just a little note there of how those connect to each other and why it connects. That's through the area of the triangle. So now we have V times W, and this works. So if you calculate the cross product, it ends up being a 0 vector. So both the cross product is a 0 vector. So it's 0, 0, and 0. That's a 0 vector. Null vector, like null vector, it could all kinds of names. That you know that sine of theta is also 0. So this is also going to be 0. So if this is 0, then they're going to be the angle between them is 0. So that means they're actually parallel to each other. They're the same. They're in the same direction. The two vectors. One of them is the multiple of the other. So that, for an example, that would be 1, 1, 2, and 2, 2, 4. Because 2, 2, 4 is just a direct multiple of 1, 1, 2. And yeah, that's that one. Next we have the vector equation of a line in 2 and 3 dimensions. Now that's that's useful. So let's jump into the sketch. So if we were to have a line, so the way the vector equation of lines work is it's usually in the general form r is equal some vector plus some parametric. Yeah, so that's a constant scale multiple of this vector. Now this is where the direction vector and position vector thing comes into. This is a position vector. This is a starting point. Also, pardon my horrible handwriting. This is position. I can't write, but position. This is a position vector, and this right over here is a direction vector. This is a direction vector. So this is your starting point to where you're starting, and this is the direction at which it's going. So you start at this point, then you move back and forth as t can change and be any value at all, and you call this a parametric, basically, for HL, which this will become useful much later for HL. But this is any value. It's a parametric that can be any value and controls the direction vector. So let's think about it. In 2 dimensions, this is super simple to think about. So let's look at the vector. There we go. R is equal to 1, 2 plus t 1, 1. Right. So what we would do is we would look at the point 1, 2. So let me actually draw this correctly. I have this not horrible. 2, So let's look at the point 1, 2. So it's 1, 2. It starts, that's a position vector. It starts there. And then from there, you can go any direction 1, 1. So you want to, then you draw the direction vector 1, 1. So now this is a 1, 2. The direction vector 1, 1 will reach to this point. If t was 1, if t was 1, you would add 1, 1. And you would reach this point over here, like that. If t was negative 1, you would go the opposite direction of 1, 1 and go there. If t was 2, then you would go farther away in that direction. If t was negative 2, you would go in that direction. And if t was negative 3, you would go all the way down to there and have it over there. So that's where you're tracing out this little line over here as you change the values of t and how much you're stretching out the 1, 1 in every direction. And if you notice, this is actually equivalent to saying the line y is equal to x plus 1. It's the same line. Intercept of 1, y equals to x, slope, which is 1, 1. That's it. That's literally it. And this is and then you have to notice one more thing, which is that there's no unique vector equation for any line, okay? Because you can have a multitude of position vectors which are your starting points. So you could start at 1, 2. You could have started at 0, 1. You could have started at negative 1, 0. You could have started at negative 2, negative 1. Any of these points you could have started at. You could have also had any position vector, any direction vector as well. So you didn't necessarily have to have 1, 1. You could also made it 2, 2. You could have made it 3, 3. Any multiple of this also works. So you actually have it like a large infinity of solutions to what the vector equation is, and it's just up to you what you choose as to what's the most convenient for your context, or like whatever just came up the easiest usually works out the best for a vector equation. Now, in terms of like the vector equation in the 2 dimensions didn't seem actually very useful, because this is a pretty complicated way to say something really, really simple right over here. But it is useful once you enter 3 dimensions. So in 3 dimensions, you have all kinds of really weird things happening. So if you would draw 3-dimensional axes, wow, I couldn't even intersect 2 lines. Say that's z, say that's y, say that's x. So we can have any point at any point, and then so this will be a direction vector somewhere at some point, and then you would set some direction vector, and you could actually have that's a position vector there. You can have some direction vector that spans the line over there, and that's when it gets very useful in understanding. So that's when it's much more useful. So you have some position vector x, y, z plus some parametric a, b, c, like so. Now notice that this gives I'm just going to check what curriculum I'm going into and whether it's SL or HL. Okay, cool. Okay. Now notice this can be written a little differently using some of the rules we learned earlier. So we run the rule that you just keep x, y, z for now. We learned the rule that the scalar, any scalar, can be put into it. So it can be TA, TB, TC, like so. So R is equal to x plus TA, y plus TB, z plus a, z plus TC. Notice I can't even read my own handwriting. That's how bad it is. This is another way to dictate the thing. Actually, I should have used different values for x, y, and z, so that this would I would just avoid ambiguity. I'm just going to do that really quickly, just better. Just one second. Just give me a second. I'll use better. I'll be better. I'll use S. I'll use S, U, and V. S, U, V. S, U, V. Notice now, x is equal to S plus TA. Y is equal to U plus TB. Z is equal to V plus TC. This is the parametric form. this is the parametric form of these. So it's defining x in terms of some changing thing, y in terms of some changing thing, z in terms of some changing thing. And this is your parametric form for the equation. So you have your vector form over here for a line. You have your parametric form right over here. So let me just go check out the formula booklet to see if you have that right over here. So your vector, so we have a vector equation of a line. I think you have vector. Yeah, so you have a vector equation of a line, which is a, which is some vector, b, some vector, and over here they actually use lambda as defining that vector. So lambda, they use lambda instead of t. But I use t, they use lambda, same thing. It's just a parametric. So this is a parametric form of the equation of a line, which I just derived for you. Instead of using s and some random variables, they use some better variables. So x is x naught plus lambda l. So whatever the terms of the vectors were over here, we put it into here. So you can try and derive yourself, get from here to here. So get from there to there. You should try and derive that yourself when you're trying to do it. Now, the last thing that you can do is that you should notice that something that we can do, which is really interesting with these, how we derive the last Cartesian equation of a plane. So notice that x equal to x naught plus lambda l, right? So we can write everything in terms of lambda. Lambda is equal to x minus x naught over l. So x minus x naught over l. And then we can also write, again, lambda is equal to y minus y naught over m. And lambda is also equal to z minus z naught over n. Since all these are equal to each other, we can literally just set them equal to each other. And this is also an equivalent form of a line. So this we would call the Cartesian equation of a line. And these three different equations of a line that are important for the IB. And yeah, that's basically it. Okay, so these all give you important little snippets of information, but let's just think about what we can derive from each of these equations. So if you had this equation, you know position vector and you know your direction vector. Now, if you knew your parametric form of the equation, your position vector is now hidden in the x naught, y naught, and z naught. So x naught, y naught, z naught, that's your starting position vector. And your direction vector is hidden in the L, M, and N. So you have L, M, and N. That is your direction vector. Same thing, hidden right over here in the Cartesian equation. L, M, N. The same L, M, and N go here. And then it's the same over here, x naught, y naught, z naught. They all go over here. Notice this is a minus x naught, minus y naught, minus z naught. So if you had a Cartesian equation telling you x minus 2 is equal to y minus 3 is equal to z minus 4, it would not be negative 2, negative 3, negative 4. It would be 2, 3, 4, like that. Okay? So that's the information that you gain from these little equations here. Let's jump back. So check. Oh wow, it's just me alone. It's okay. I'm sure someone will watch this at some stage. So the next thing we have over here is the 1 second. Is no one watching this? I mean, I'll continue. Someone can see this later. Yeah, that's fine. So now I have the positions of lines, coincident, parallel, intersect. So now you have various different things. So now using these different forms, you can try to understand the relationships between two different lines. So the position line, coincident, parallel, intersect is key. There's no one watching. There's not much like. Okay. If two vector equations have like the same, what am I doing? Wait, let me think about this. if they have like the same, if they land on the same line, like they are the same line, then they're coincident. Now, the way you would know that is, one, their direction vector has to be a scalar multiple of each other. So they have to make sure that that the direction vector actually lands on that. So if we had, like, say, it's like, we'll draw a little thing. So I'll have a screen sketch here, and we had wait, so just do that. R is equal to x naught, y naught, z naught, plus lambda L and N. What you would check for is that the L and N are the same, so or at least a multiple of each other. So you need to make sure the direction vectors are the same. Now, if you know the direction vectors are the same, you know that they're parallel. So if the direction vectors of the vector equations are the same, you know that they have to be going in the same direction. They're parallel. They'll never meet each other. And then the other thing you have to check that is the starting position the same, or does the starting position of one of the lines lie on the other line? And you can check if that one of the starting position lies on the other line by literally, like, you can plug it in. You can plug it in and solve. So say I have some vector A, B, C, and I wanted to check if it lies on this line. What I would do is I would literally set A, B, C equal to x naught, y naught, z naught, plus lambda L M N. Notice, I know what L is, I know what M is, I know what N is, I know what x naught is, I know what y naught is, I know what z naught is. The only thing I don't know what lambda is to get A, B, C. Then I would plug this in, try and solve for lambda. If there's no solution for lambda, that means that ABC does not lie on lambda. If there is a solution for lambda, then that means that ABC does lie on lambda. Does lie in this vector equation. So that's, you can also check if they're actually coincident with each other. You can check they're parallel with each other by checking what the direction vector is. And yeah, so the other thing I need to check is that yeah, so, and then do they intersect with each other at any point? So you need to set them. So you would do what you can do for two different equations. Let's draw this in the sketchpad. Why doesn't this open? We have x naught, y naught, z naught, plus lambda 1 lmn. You can set that equal to another vector equation, x1, y1, z1, plus lambda 2 L1, M1, N1. Just differentiating these. Solve for this. Try and solve for this. Because we know almost all of these things. You need to check if depending on how many solutions for lambda there are, shows like whether they intersect or not. So if they if lambda 1 and lambda 2 have one solution, then you know that they intersect. So that's for one solution. If there's an infinite number of solutions, then that means that they coincide with each other. And then so that's one thing. Then if these two, the direction vectors, are not parallel to each other, are parallel to each other. If they are parallel to each other, they're the same thing but a multiple of the other. Then even if you find one sol, then it means that they are parallel. If direction vector is the same, basically the same. So yeah, that's how you figure out this stuff. And if there's no solution to it, if there's no sol to it, there's no solution, and this is not true, they are not parallel to each other, that means they are skewed, which means they're not parallel, they don't land on each other. And if you notice, in 2 dimensions, that's almost impossible. If they're parallel, they will not intersect. If they are not parallel, then they will intersect. But in 3 dimensions, for 2 lines, if they are not parallel, they can still not intersect. They still might be going in completely different directions and they'll never see each other. Yeah. Okay. Okay. So the skew thing about them not intersecting each other at all, that's something that's HL material. So yeah. Now the rest is all HL material. If anyone's still watching, no, nobody's watching. This is amazing. I don't know what the point of the session is. Perhaps someone will watch this at some stage. So I'm gonna quickly go through it. If someone else wants to at some stage watch these sessions, then you can do so. So yeah, and I think I'll find some way to change the timings. But yeah, so the vector equation of a plane, that's important as well. Again, it comes up in the over here. Notice that now you have it's very similar to the vector equation of a line, which is when you have a plus lambda some vector. But over here now you have two different scale, like changing numbers, which is lambda and mu, doing it. So that should actually make sense to you if you have a plane in 3 dimensions. So let me just show you what that would look like. Sort of. I'm gonna try my best to like try and like show this. It should be okay. You have some line. You have some vector starting over there. That's your position vector, right? So now when we figured out that we could draw a vector line equation, so we have some vector with some like scaling factor, some parametric that gives us this line right over here. Now the more important thing is now we have the ability to add another vector to this. So from every point that we've stretched out from the original position vector, we can do another scaling in this direction. So we have like several scalings in several directions. So we have an infinite number of lines created upon this line. And that's what a plane is. We have a massive plane right along here. And then in this direction, all the lines across that plane. And then we created an entire plane. And that's why we have two. So this is kind of like, the technical word is a span. So when something goes across an entire like page. So if you have a position vector and then you have some parametric multiplied by a direction vector, you know that parametric is spanning that line. This vector equation. This vector equation is spanning a plane because you have a position starting point, and then you have two vectors that are able to span an entire plane in 3 dimensions. So yeah, that's the thing. So that's all. Sorry. Yeah, that's your vector equation of a plane. Now go here. Now we have to think about the normal vectors. So one important thing about how we define planes is that there's another way to define it that doesn't involve having this vector equation specifically. And the way to define a plane in that way is what is the normal to that plane. So the normal to a plane is a point that is perpendicular to the plane entirely. So what you would do is you would have some plane like so, and some point in that plane, and something shooting out of that plane like that, that is perpendicular to this plane, right? That, and it's shooting out. The vector that defines that plane is called the normal to this plane in that region. Now the normal, remember, because this is the direction. It could be, there's an infinite number of normals, but this is what the vector would look like. So for this perpendicular, so for any plane, we come up with a new form of describing it, which is ax plus by plus cz is equal to d, where the vector a, b, c is the normal to the plane. So that's the line that's perpendicular to the plane. Notice, and then you can basically use that normal to like maneuver around the plane. So if you change the normal, then the plane would change its like direction entirely. And then depending on what the value of d is, it depends how you change the position of where the actual plane is. So yeah, that's what it would look like. And that's the vector equation of a plane. So now this is actually this information is actually useful, like what the normal is, like the fact that when we define the normal define the plane in terms of its what is perpendicular to it, that's useful because sometimes the IB will ask you if you have these two vectors that lie on this plane, some vector A and some vector B that lie on this plane. Remember, A cross B is equal to the normal of the plane that contains A and B. So if A and B are contained in some plane, if we did A cross B, that would give you the normal to that plane. And that's what the main use of finding something is. So if IB gave you something A0, A1, A2, and some vector B0, B1, B2, across them, you can figure out what the equation of the plane is that lies in this thing by finding out what the cross product is. And you would find the cross product. The cross product is ABC. So the cross product, this whole thing gives ABC. If it gives ABC, then we know that the plane has an equation of the form AX plus BY plus CZ is equal to D. And then the D we would have to calculate by checking one of the points in the plane actually there, because then there's obviously an infinite number of points, infinite number of positions that the plane can be in for that direction specifically, but you need to find out what specific point it contains, and then you'll be able to figure out what the plane is. Okay, so that's there, and then we have that's we discussed the normal vector. We discussed the Cartesian equations. The Cartesian equations right over here. So that's how you figure out for vectors. So you need to think about your normal and your Cartesian equations. So always when you're thinking about vectors, think about what information do you know, what's like the perpendicular things, like cross products, dot products, all the different pieces of information, what they're giving you. It's like solving a little puzzle of how to solve a problem. And you gotta crack the puzzle. So then next one, so it's intersections of lines and planes plus angles. So I think I really should just find some good questions as well. But yeah, so intersection of lines and planes plus angles. Let me just actually find a question that'll do this. I apologize, I didn't do this earlier in the session, but let me just do that now. I'll find current vectors such as form. Actually, yeah, let's not. I think I have an understanding of what to do. So I already discussed the intersection of planes earlier, and now I'm going to discuss how you would intersect planes together and what their solutions would look like. So when you're intersecting planes with each other, there's various different things that planes can do. So the planes can be completely parallel to each other. One second. I think I need to use a question instead. Here. Okay, this is good. Yeah, this is better. I didn't discuss one last equation of a plane. I think I forgot. I don't know why I forgot this. Using R and A and yeah. Okay. A times A dot n R dot n A dot n. Okay. Point of the equation line is x. That's fine. Yep. Okay. I think I got it. What is that? Lambda 5 minus section line. Just give me a second. I'm thinking about something. Intersect in the line. -1 minus 5. Okay, yeah. So let's just think about this one. So what they're doing over here is that they're asking, they have two planes that they intersect in some line 5x plus 5x plus lambda 5x plus 1 minus 5y equals minus 5z. So what they did to find out the points at which these each one is intersecting, what they did is they checked. They looked at, they said 5x plus 1 is equal to some constant scalar lambda, which is a parametric lambda. Then you have some 9 minus 5y, which looks into some parametric lambda. And then negative 5z, which is also some parametric lambda. And then they calculated and got these three values right over here. And that's how they figured out what the values are. So then they asked, what is the value of k? So what they can do over here is that they know that, let me think about this. So yeah, z is equal to, yeah, okay, cool. So what they did is over here is that they plugged this stuff in. So if they looked at this equation right over here, so they looked at x minus y plus 2z is equal to k. So in order to find k, they literally plugged in these values of x, y, and z into the original equation, and then they found out what the value of k in terms of lambda. Then once you like solve for all of this stuff, and then you can do the same thing for the other plane, then you can find out what k is using a system of equations, and then you get k equals -2. Okay, this is this is not the kind of question I was searching for. Equation. One sec. Okay, here. Okay, this one's nice. I think this one's going to be a good one. Okay, yeah, this is not bad. And this one is finding the angles between different. Actually, no, I don't even want to do this one. Is anyone still watching? Yes, at least one person is watching. So your two planes intersect line. Oh, this is the exact same question. How did they get the exact same question twice? This one looks much nicer. Okay, yeah, so we have two planes right over here. Now you can actually try finding out what angles are between these planes. The way that we find out the angles between planes is that we check with, why does this not work? We do this. So the way we would check, so we would look, we know this plane has a normal vector, and that normal vector is 1, minus 2, minus 3, which we get from the coefficients of the Cartesian form. And we know the other vector is 2, -1, -1. It's 2, -1, -1. So what we would do to find the actual vector, the cross product between these, to find the angle between these two vectors, because these are the perpendicular to it. It's equivalent to finding the angles between these two is to find the angles between these two. So if you find the angles between these two, you would use the dot product formula we learned earlier. So if you can see over here, they use it, cosine theta is equal to n dot m over the magnitude of n, the magnitude of m. So that is in your formula booklet. Then you can calculate that whatever theta is 0.702 radians or whatever. So this is going to be a paper 2 question because these aren't very simple values that you're calculating. So yeah, so then we have the planes intersect in a line, line L1. So the vector equation is this over here. The way that we would do that is you would let's just erase this and actually wait, I should get out of this mode and look below. So the way that they do that is by they convert it into a different form. So they combine these. They find 5x minus y, so 3k minus 2, and then they find some way of like understanding x in terms of k, and then they do this. This is the algebraic analytic method mainly. I have a feeling that's what this is. 1 second. Yeah, so they're showing the equation and doing some algebra. So this, I think I would generally have used this one more. So the vector equation of the line, so that's negative, and then I would cross product it. I would find out that and so the direction of that line is 1, 5, -3, and then I would let x equals 0, like set and solve simultaneously for what the equations are. You need to look more carefully at these mark scheme solutions, and if you have any issues, then you should just like DM me or like ask on Discord. There's way too many vector equation examples, and the best way to do them is to just keep practicing them, and then you'll get used to them. So yeah, I don't think there's no one watching right now anyway, so I'll leave topic 5 for tomorrow. Okay, that's it.